In the next two videos, we're going to be looking at proving some basic theorems of set theory. Now, there's a multitude of theorems that we can prove, and there's various techniques, so we're just going to highlight some of them in these next two sessions. So the first theorem is about equality of a set. Now, we've got an intuitive understanding of what it means for two sets to be equal. It means they've got the same elements in. They look the same in all ways, shapes, and form. Now, it's not always easy just to identify the elements, so this theorem can help us to prove sets are equal if we don't have enough information to just compare them element by element. So we're saying two sets are equal if and only if set A is a subset of set B and set B is a subset of set A. Now, to prove an if and only if statement, very often it's easier to break it into two implications, in the one direction and in the other direction. So in the first direction, we say, well, if it's given that A is equal to B, we want to now show that A is a subset of B and B is a subset of A. And in the other direction, we say, well, if it's given that A is a subset of B and B is a subset of A, we want to then show that A is equal to B. So let's take a look at how we're going to approach both of these. So in the first direction, we say given A is equal to B. Now we want to show a subset concept. Now we know the definition of a subset, and the safe place to go is to definitions, to do proofs. So if I want to show that A is a subset of B, I just choose an element of A. Now we want to show that that is also an element of B. Then we can conclude that A is a subset of B. Well, let A be a subset of A. We can then say, therefore, A must be in B because of what is given, since A is equal to B. So therefore I can conclude that A is a subset of B. Not much to it, but we have to go through the process. Similarly, if I choose some element of B, then I know that B must be an element of A because I know that A is equal to B. So now I've shown that B is a subset of A. So we've done it in the one direction. So let's look at the other direction. Given A is a subset of B and B is a subset of A, we want to show that they're equal. Now, from the definition of subset, if A is a subset of B, I know for every x in A, and whether you use x or A or B or Y, it's just a placeholder, just a letter, a variable. For every x in A, x must also be in B. That's from the definition of subset. And for every y in B, y is also in A. Same definition of subset. So that information is given. So every element in A is also in B, and every element in B is also in A. So my conclusion is that A is equal to B. So now I've done both directions, so now I can bring it together and say A is equal to B if and only if A is a subset of B and B is a subset of A. All right, let's look at another technique. A without B, or the difference between A and B, however you define that, is intersection with B without A. It must be an empty set. Now, just for notation, remember the difference. A without B, we also write as A without B in that way. So whichever notation you're using, those mean the same thing. Now, a very nice technique to show that something is an empty set, very often a proof by contradiction. We can call it an indirect proof as well. What we're going to do is we're going to assume that there is an element in that set. So let's assume that there's some element of this set, A without B's intersection B without A. I'm assuming there's something in there. Now, I'm going to see what the definitions, where they lead me, and if it leads me to a contradiction, that means my original assumption was wrong. So then there can't be an element in that intersection, so it must be empty. So that's a proof by contradiction. So let's look at what the definitions tell me. If A is in the intersection of two sets, then we know A must be in the first set, and we can use a symbol or the word, A must be in the second set. Now, how do I know that? That's the definition of intersection. Now, just take note. It's important to know why you can say that and to have your reasons. Now let's look at where the definition of without, or the difference between two sets, what that means. If A is in A without B, that means A is in A, that lowercase a is in set A, and A cannot be in B. That's the definition of without. And similarly there, A must be in B and A cannot be in A. And that's the definition of the difference between two sets. So let's see what I have there. I've got a lot of ands. If I look at these as statements, and I'm going to just write it down here, so it just makes a little bit more sense with not so many words. If I've got a statement P, like A is an element of A, that's a statement. P and A is not in B. I can think of that as not Q, not P is in B. And A is in B, so that's the statement Q, and A is not in A, so not P. Here I've got a bunch of statements, P and Q and not P. Now we know from our truth tables and our section on logic that this is a contradiction. This can't be true because I can't have P and not P, Q and not Q. They cannot both be true. So that is a contradiction. And sometimes we use the symbol for contradiction, or you can say contradiction. So it's a contradiction because A cannot be in A and not in A. It's either in there or it's not. It can't be both. So that's a contradiction. So the conclusion I can make is that that intersection is then empty because I took an element from that intersection, see what happens, and that led to a contradiction. So my only assumption I made here is that I've got an element in that set and I don't have one. So therefore the intersection is empty. All right, let's look at one more proof by contradiction. If A without B is the set A, then that intersection of A and B is an empty set. So now we already know how to do a proof by contradiction. You can try this on your own, set it up and see where it leads, or you can follow along. So we're going to say, assume X is an element of A intersection B. And whatever you call it, whether you call it A, B, X, Y, that doesn't matter. I'm just choosing an element in A intersection B. So now I'm hoping I can get to a contradiction, which will mean that my original assumption is wrong, so that intersection has to be empty. So let's take a look. What does the definition of intersection tells me? That tells me that X must be in A and X must be in B. That's the definition of intersection. All right. Now, this statement we're given that A without B is A. So if X is in A, that means X must be in A without B. So I'm just replacing that first part. The next part just drags along. Where's that from? It's given that A without B is equal to A. All right. So if X is an element of A without B, then that means X is an element of A and X is not an element of B. And X is an element of B. How did I expand that? By using the definition of the difference between two sets. So here's my contradiction, because X can't be in B and not in B at the same time. So that's a contradiction. So my original assumption is wrong. So A intersection B is therefore the empty set. Right, in the next video, we're going to look at proving one of De Morgan's laws and one of the distributive laws. They get a little bit bigger and messier, but we will see on how to prove those theorems in set theory.